So this is the culmination of all the chemistry that we've learned and all of the basic information about the Big Bang that we learned, all right? So if you remember back to the Big Bang, the three elements that formed right after the Big Bang, 380,000 years after the Big Bang when that light was emitted, was mostly hydrogen, like 99% of the elements were hydrogen, maybe even more. Some helium and very little lithium. Now, if we go back to the periodic table, you'll see that we've got hydrogen as the first element, helium is the second element, and lithium is the third element. So the point is that the universe wasn't able to make these things yet. So they were just able to make these really light elements, 1 proton, 2 protons, and 3 protons. They couldn't get any more protons together. Now don't get me wrong, there probably were some berylliums, there probably were some borons, but those would be in such small amounts that we can't detect them and we can't measure them, okay? So, stars are literally element factories. So they're super hot. Now, when we burn a match or we catch anything on fire, fire is the process of chemical bonds, either breaking or coming together and forming. So it's usually both at the same time. And what's happening is we're not changing the element, right? So if we're burning a hydrocarbon, which just means hydrogen and carbon, what's happening is that there's a chemical made of hydrogen and carbon, and then there's oxygen in the air. When the oxygen in the air and that chemical reach a certain temperature, the oxygen is able to go in and break apart that hydrocarbon, which releases a tremendous amount of energy and tremendous amount of light, right? So that is a chemical break. What's happening inside of stars is a process called fusion. So fusion is not a chemical process. It's not breaking bonds between elements and making new bonds between elements. It's literally taking two elements, squeezing them together under such tremendous amounts of heat and pressure that they fuse and create something brand new. So chemical bonds or fire doesn't make necessarily new elements. It just makes new combinations of the elements that already existed. Fusion inside of stars takes elements and squeezes them together to create new ones, right? New elements. The difference between a chemical reaction and a fusion reaction is like the difference between someone who has $100 in their bank account versus someone like Bill Gates, right? Someone who's a super billionaire, all right? So like these are two major different processes, which is why stars are literally like billions and trillions of degrees on their inside sometimes. Okay? So this is the complicated part. You're not going to have to memorize this whole thing, but I'm going to give you a visual demonstration of this. So the main idea, stars are composed of mostly hydrogen and helium, two of the most abundant things in the universe from the beginning and even now. So a lot of that helium that forms or that exists inside of a star forms from the hydrogen fusing. Okay, so the hydrogen fuses with other hydrogen, and the more hydrogens fuse with other hydrogens, and eventually we end up with the helium. So here's how it starts. Like I said, two hydrogens fuse together to form this thing called deuterium, right? So as these hydrogens fuse together, one of the protons that fuses becomes a neutron, okay? So deuterium is a proton with a neutron next to it, and then one electron around the outside. So what happens there is that one of the protons and one of the electrons combines to form a neutron. That's just something that can happen. It's crazy, but it's something that can happen. So that's why we end up with a deuterium, which is really just a heavy hydrogen. So it's just a hydrogen, right, one proton with a neutron attached to it. So that's step one of fusion. And yes, that produces a tremendous amount of energy outward in the form of light and heat. Now this heavy hydrogen, or this deuterium, fuses with another hydrogen, creating an unstable helium, helium-3. So if we go back to the periodic table, you'll see helium likes to be at a mass of, or a atomic weight of 4. So this is saying that the second step of fusion creates a helium-3, meaning that it's got 2 protons with 1 neutron on the outside, but it likes to have 2 neutrons. All right, so that's missing. So eventually it fuses with another helium, right? And that forms a helium-4, plus it spits out 2 protons and 2 neutrons. So this is the type of fusion that happens in all stars, and here's the actual visual. So we start with 2 hydrogens fusing. One of the electrons and one of the protons, so like one of the electrons that goes around this, one of the electrons that goes around this, one of them clashes into the other proton, turning it into a neutron. So now we have a heavy hydrogen, or a deuterium. These combine, it spits out some particles. This is just like energy essentially, and matter that we don't need to worry about right now. And it just produces a deuterium. This deuterium finds another hydrogen and fuses, producing some other stuff, but the main idea is that this ends up inside with the nucleus, and that fuses to form helium-3. Unstable. The helium-3 finds another helium-3. They fuse. Fusion's a little messy here. It spits out 2 hydrogens, and we end up with 1 helium, 1 stable helium. So as a star gets older, it turns its fuel, its hydrogen, into helium. And then eventually they run out of hydrogen and the star dies. And that can happen in multiple ways, depending on the size of the star. So just to be clear, it takes 4 hydrogens, right? 4 hydrogens in the beginning. Really, if you want to think about it, 6 hydrogens, because we have these going in as well. But 4 hydrogens, because we end up with 2 hydrogens at the end just spit out. So it takes 4 hydrogens to make 1 helium in the process of fusion inside of a star. So just to review, we fuse hydrogen to make deuterium. Deuterium becomes a light, unstable helium. Then the heliums fuse to form our regular stable helium and 2 stable hydrogens. So it ends up stable, which is why the universe is calm, I guess, right? So again, it takes 4 hydrogens to make 1 helium. So why is that? Look at the atomic weight of hydrogen. Look at the atomic weight of helium. It takes 4. All right. So our star. So our star is an average sized star. It uses hydrogen to fuse into helium, just like we saw there. And that's about it. At the end of its life, it may start to fuse heavier and heavier elements, but eventually it will die, right? So heavier elements such as oxygen and carbon, eventually it will die and become a white dwarf. So that's the death of our star. As the sun runs out of fuel, the core of the star begins to shrink, increasing the amount of fusion, creating an outward pressure. So there is a force outward because fusion is an explosion. A hydrogen and a atomic bomb are outward explosions. That's exactly what's happening inside of a star. So that pushes the outside part of the star to become bigger, where it cools off, and it becomes a red giant. So it goes from a white star to a red giant, cooling off. But it becomes brighter because it's bigger, all right? So eventually, the outside ends up just getting lost into space, and the inside ends up as a white dwarf, okay? So the core is left over, and this outward expansion causes the star to just kind of, the outer part, like this whole outer part just ends up, being spread out and dispersed through space, while the white hot core remains for trillions of years, or for about 1 trillion years, okay? All right, so here's your fusion. 4 hydrogens become 1 helium, and we get a lot of energy and other stuff to come out. All right, so what gives a star its size? So our star has fusion happening at a very consistent rate. So consistent fusion leads to a consistent size of a star. But if we had more fusion, so fusion creates an outward explosion on the star. If we had more fusion, it would overpower some of the gravity, making the star bigger. So in a lot of cases, not only do big stars have a lot of size just because they have a lot of stuff, but they have a lot of fusion, which creates it to go outward, right? Now, as the fusion, explodes outward, gravity is counteracting that, creating a balance, Newton's third law. There's a balance of forces keeping the star at a consistent size. Now, what happens if fusion begins to slow down? If fusion begins to slow down, we have less explosions outward, so the star begins to shrink. And this is what happens at the end of a giant star's life. So our star does the opposite. Since it's an average-sized star, fusion ends up happening and more because the core begins to collapse at the end of its life, creating more of an explosion outward, causing the outside of the star to just grow. Giant stars have less fusion. It actually drains itself of fusion, and this ends up causing less explosions, causing the outside of the star to collapse, huge amount of force on the inside, creating a supernova. Okay, so I'm going to stop here, and we're going to learn about supergiant stars next.